So in this experiment, we will study the electromagnetic induction. When there will be relative motion between coil and the magnet, there will be generation of EMF inside this coil, which follows the Faraday's law as given here. So which states that when there will be a change in flux linking through the circuit, there will be an induced EMF. So when there will be back and forth motion between this magnet and this coil, the magnetic flux density will follow this curve, and the induced EMF for each half of the cycle, it will follow like this. So one half it will be negative, and the other half of the motion, the electromotive force will be positive. This is the experimental setup to demonstrate electromagnetic induction. So it consists of one bar magnet suspended on this circular arc of radius 40 centimeter, and these are the two coils which are connected in a series, and turn number of each coil 4500, and the resistance of each coil 500 ohm, radius of curvature 40 centimeter, and internal diameter 3.67 centimeter, external diameter 4.88 centimeter. This is the circuit board. It consists of following components: resistors of different resistance, and these are the diodes. This is the ammeter, and these are the capacitors, and this is the digital voltmeter which measures the DC voltage. So the resistance of each resistors are given in this diagram. So we have different varieties of resistance: 2.2 kilo ohm, 5.6 kilo ohm, 15 kilo ohm, 500 ohm, 50 kilo ohm, and this indicates this is the schematic of the diodes on this circuit board, and these are the different capacitance of these capacitors. So these are all electrolyte capacitors. So we have to keep in mind while we do the circuit connection. So we have to properly connect the terminal, positive and negative terminal of the capacitor, because this electrolyte capacitor, has distinct polarity. So here we have 580 microfarad, 100 microfarad, 470 microfarad, and 1000 microfarad capacitance. And this DC voltmeter can measure DC voltage from 0 to 20 volt. And this ammeter can measure the current flowing in this circuit. This is the stopwatch to measure the time period of the pendulum.
So the first part of this experiment is to study the EMF induced as a function of velocity of the magnet. So as we know that the angular velocity is given by this formula, that is 4 pi by t sine theta naught by 2, where t is the time period of the pendulum and theta naught is the angular amplitude. So the maximum linear velocity of the magnet is given by r omega max, where r is the radius of the arc. So here we have two unknowns, that is t and other one is theta naught. So in the first part of this experiment, we will measure the time period of this pendulum.
So for the first part of this experiment, we will measure the time period of this pendulum. For that, we will make some angular displacement. Let's say here we have made a 30 degree of angular displacement, and we will allow it to oscillate. So when this pendulum will reach to the same point, this is called one oscillation. So what we will do here, we will measure the time period of this pendulum for certain number of oscillation. So to take the readings, what we will do, we will measure the time period for, let's say, 10 number of oscillation. For that, we will make some angular amplitude, let's say here 30 degree, and we will allow it to oscillate, and we will start the stopwatch. 2, 3, 4, 5, 6, 7, 8, 9, 10. So what we get here? 16.75 seconds. So in the next reading, we will make some other angular amplitude, let's say 20 degree, and we will allow it to oscillate, and we will note down this time for 10 oscillations in this stopwatch. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here we have obtained a time of 16.87 seconds, which is similar to the previous reading, that was 16.75 seconds. So this is time taken for 10 oscillation. So time period is obtained by taking average of these oscillations. So time period is the time taken for one oscillation. Here time taken for 10 oscillation is 16.87 seconds. For one oscillation it will be 1.687 seconds. Similarly, we will perform this experiment for different angular amplitudes, and we will obtain the time period, and then we will take the average of those time period, and we will get the final time period of this pendulum. Let us make the circuit connection to perform the first part of the experiment. So we will make circuit connection using this circuit diagram. So for connecting the circuit, we will use connecting wires. So these are the connecting wires here. So we will use these wires to connect the circuit. To make the circuit connection, we will connect this coil with resistor. Here we have two coils connected in series, and this coil have two ends. I will connect one end of this coil with the resistor. So here using this connecting wire, so one end is here, and other end I am connecting with 500 ohm, that is this one. Other end of this resistor is connected to this positive end of the diode. So other end of this resistor is connected with positive terminal of this diode. So I have connected it here. Now the diode is connected with positive terminal of this capacitor. So positive and negative terminal of capacitor are indicated with red and black. Positive one is red one is positive and black one is negative. So other end of this diode is connected with positive terminal of this capacitor. Then the negative terminal of the capacitor is connected with emitter. So negative terminal of this capacitor is connected with emitter. Now I will close this circuit by connecting this emitter with other end of this coil. Then I will connect this emitter with other end of the coil. So due to the relative motion between the magnet and the coil, a current will flow in the circuit due to production of this induced EMF, due to which this capacitor will charge. And to measure this induced EMF, we will connect a DC voltmeter in parallel with this capacitor. So this is the capacitor and this is the voltmeter. I will connect voltmeter in parallel with this capacitor. So here, this is connected here and here. So our objective is to get this induced EMF as a function of velocity. At present, there is no relative motion between this magnet and the coil, so there will be no induced EMF in the circuit, which we can see from this voltmeter, that is 0 volt. So here what we will do, we will make some angular displacement, let's say 30 degree, and then allow this relative motion between the coil and magnet, due to which a EMF will be induced in the circuit, as we can see, and this capacitor will start charging, and we will note down the maximum value of this EMF induced. So the maximum EMF is 1.51 volt. Using this angular amplitude, that is theta naught, and the time period that we have obtained previously, we can obtain this maximum velocity. Then using this maximum velocity, we can plot the induced EMF as a function of velocity.
So in the second part of the experiment, we will determine the value of an unknown resistance by studying of charge accumulated in a capacitor over a time interval through electromagnetic induction. So here what we will do, we will charge the capacitor which is connected in a series with this coil, and this capacitor will be charged while there will be relative motion between this coil and the magnet, and we will measure the induced EMF across this capacitor for a time interval t, and from there we will try to estimate the unknown resistance connected series with this circuit. So when there will be relative motion between this coil and magnet, there will be change of magnetic flux which will generate electromotive force inside this closed circuit, and this capacitor will be charged due to this electromotive force, and we will measure the induced EMF across this capacitor using this voltmeter, and we will calculate this charge accumulated across this capacitor from the induced EMF using this formula. Now let us perform the experiment to determine the unknown resistance in this circuit.
So keeping the same circuit connection as in the first case, now in this case we have replaced the resistor, known resistors with an unknown resistance. So this resistance we have used. Now in the second part we will measure the induced EMF across this capacitor for each number of oscillation, and we will determine this unknown resistance value from the experimental results. So we will give an initial angular displacement of 30 degree, and we will measure the induced EMF for each number of oscillation, and we will record this induced EMF as a function of oscillation, and convert this oscillation number of oscillation in time.
So here we measured the induced EMF as a function of number of oscillation, and we converted this number of oscillation into time by multiplying the time period of the oscillation. So finally you have to plot the measured induced EMF as a function of time, and from this induced EMF you can calculate the charge accumulated across the capacitor, and you can plot this charge as a function of time, and from this plot you can estimate the unknown resistance connected in the circuit. So as we can see, the measured value of the unknown resistance connected in the circuit as 49.36 kilo ohm, and also we will estimate the unknown resistance from the recorded experimental data using the charging of a capacitor, and we will see there will be a discrepancy between the estimated value of the unknown resistance from the data using the charging of a capacitor, and from the measured value of the unknown resistance using this multimeter. So all of you try to figure out why this discrepancy arises when we use this charging of a capacitor formula and applied in this case for electromagnetic damping case, but we are getting a discrepancy between the measured actual value and the estimated value from the experimental data.
So this is the third part of the experiment, and now we shall study the electromagnetic damping. If we give the pendulum an initial amplitude and leave the pendulum, then it will start oscillating. However, after some time we will see that with each oscillation the amplitude decreases. This phenomenon is called damping. Now there are many reasons for this damping. There is always some air resistance. Then again, the system is not nearly free from friction at the point of suspension. But the most important source is that the induced EMF in the coil itself introduces damping through a mechanism which goes by the name of Lenge's law. This law states that the direction of the induced EMF is always such as to oppose the change that causes it. Now we shall study the electromagnetic damping which is occurring in this setup. Now we will study the various configurations of the circuit for damping. There is open circuit damping, closed circuit damping, damping with the resistor in the circuit, and damping with the capacitor in the circuit. Now we will show the open circuit damping. For the open circuit damping, we give the pendulum an initial amplitude of 30 degree. After which we release the pendulum, and we will see after some time that with each oscillation the amplitude of the pendulum continuously decreases. So now we can see that initially we started with an amplitude of 30 degree, but now clearly the amplitude is less than 20 degree. So there is a damping. To quantify the open circuit damping, after every 5 oscillation, we will measure the amplitude of the pendulum. In the closed circuit configuration, we connect the two terminals of the coil and short them using a wire. Now we will see damping in closed circuit. For this, just like in the previous case, we will give the pendulum an amplitude of 30 degree and we will release the pendulum. As we can see that the damping is greater than in the previous case of open circuit. And in a similar way, we measure the angular displacement of the pendulum after 5 oscillations. Now we will see the damping for the circuit with the circuit containing a resistance. In this case, the circuit is connected as follows. We take one of the terminals of the inductor and connect it to one end of the resistor. So what we do in the next step is connect the other end of the resistance and complete the circuit by connecting the other end with the other terminal of the inductor. As usual, we will give the pendulum an amplitude of 30 degree and after that we will release it. After every 5 oscillations, we will calculate the amplitude of the damping. In a similar manner, we record the amplitude after every 5 oscillations. In the fourth case, we will measure the damping in the circuit when an inductor is connected with a capacitor. So in the connection of the circuit, we have got one terminal of the inductor connected to one terminal of the capacitor. In this case, the capacitor is 470 microfarads, and we take the other end of the capacitor and complete the circuit by connecting it to the other end of the inductor. For this, we will give the pendulum an initial displacement of 30 degree. In a similar manner, we record the amplitude after every 5 oscillations. We study the electromagnetic damping using this table. Here we have n, the number of oscillations, theta, the amplitude of the pendulum in the open circuit configuration, in closed circuit configuration, in the circuit containing a resistance of 500 ohm and a capacitor containing 100 microfarads. We already recorded theta for every 5 oscillations. We can see that as the number of oscillation increases, the amplitude continuously decreases. This phenomena is called damping. We can see that in the case of open circuit, the damping is very low.
whereas in the case of closed circuit the damping is very high. In the case of resistance and in the case of capacitance, the damping is actually intermediate. So guys, can you tell me as to why the damping in the case of closed circuit is so high?
So from the previous table, you have to plot the amplitude as a function of number of oscillation for different cases. We recorded the value of the amplitude for open circuit, closed circuit, circuit with resistance, circuit with a capacitance, and uh, you have to plot each data with different labeling. When you plot this in graph paper, you have to label different data with different labeling, and also you have to plot the log of the amplitude as a function of number of oscillation. And from this plot you can see the different cases of the electromagnetic damping.
So we have demonstrated the electromagnetic induction and corresponding electromagnetic damping using this experiment, and now this is your turn to understand and to analyze the data and to understand each and every step of the experiment. Good luck.